Hey everybody, thank you for joining me and Alden today. We're super stoked to dive into the weeds on some ransomware that we were reversing a while back. It's called LukaLocker. We'll give it a couple minutes before we get started, just in case we have some people filtering in. But would love to hear where you guys are from. I see a lot of different places in the chat right now, so it's great to have you all.
Damn, we got South Africa. That's mighty far.
I know.
India, all over the world.
Boston, nice. I don't know if you're a Bruins fan, but I am a Florida Panthers fan, so I just thought I would mention that if you are a Bruins fan, whoever's from Boston.
We don't need no Boston slander here, Johnny. Sounds like jealousy.
Cool. All right. Well, let's go ahead and get started. Again, thank you so much for joining us today. We wanted to dive into some really cool ransomware that Alden and I kind of reversed a little bit ago, and it's called LukaLocker. So let's go ahead and dive right in. For today's agenda, we're going to make some general introductions between Alden and I, just so you can get to know us a little bit better. And then we're going to do a walkthrough through LukaLocker. This isn't going to be from start to finish reverse engineering the whole thing, but we will be walking through some of the techniques that we found that were very interesting that they implemented. And then what was also interesting about the code itself and what maybe some struggles we had when reversing it, or maybe what just kind of took longer than we have seen in the past with other ransomware variants. And of course, we're in the business of helping people understand these techniques and understand detection opportunities. So lastly, we're going to dive into telemetry and detection opportunities. These are going to be things that you can take to your own environment and you can kind of dive into and see if you can implement yourself. So to start off, my name is Jonny Johnson. I'm a principal product researcher here at Huntress, specifically focused on Windows endpoint EDR products out there. I have experience doing Windows internals research, reverse engineering. I've done consulting in the past as well. And Alden, I will pass it over to you.
Sweet. Thanks, Johnny. So my name is Alden. I am a senior detection engineer here at Huntress. My primary focus here is macOS, but I love all things malware. So a big fan of reverse engineering, malware analysis, big Binja shill. So if you follow me on Twitter, you know that I constantly talk about how good Binja is. We're gonna have some Binja talk here in a minute. But yeah, that's about it.
Sweet. Yeah, I'll also point out that when we originally reversed this, I did it in IDA and Alden did it in Binja. And because I'm so kind, I decided to use Binja for the sake of this presentation to make sure the screenshots were the same. So,
and it was out of kindness and definitely not that Binja is just better, but
yeah, exactly. Yeah. Great. Cool. So let's start off with a LukaLocker walkthrough, and Alden's going to go over the background.
Sweet. Yeah. So this ransomware, we first observed it on June 27th, so relatively recently. We saw it initially, and it's sort of been tracked also under Nebula ransomware. So you'll sort of hear us use both interchangeably. Just know that like LukaLocker and Nebula, they're the same thing. Just, you know, as with all things malware, naming is always a sort of pain point. Halcyon, which is a ransomware sort of recovery company, put out a blog post on July 1st about it. They were the ones that coined LukaLocker. It's a great post. Highly recommend checking it out, after this. But essentially, this ransomware is, in terms of like functionality, is very similar to ransomware that's been around for forever. It does target both Linux and Windows. So as you're sort of like reversing through it, you'll see some interesting artifacts of both. As a sort of weird threat group thing, there is no leak site associated with this group currently, at least one that's been observed. So when this group is ransoming organizations, that information is not being published publicly anywhere, which is sort of atypical for a ransomware group. The other thing that's sort of odd about this ransomware group is that not only do they deploy ransomware, but they also have custom vulnerable driver that they bring and a rat that they bring with them. So we're not going to cover those today, but I'm happy to chat with anyone post this talk about both the rat and the vulnerable driver stuff. Today we're just going to cover the ransomware binary itself and some of the weird stuff that they were doing in there. On the right here, you can see one of our amazing SOC analysts posted a little quick analysis of one of the events that we saw for this ransomware. So yeah, I highly recommend checking out the link there, and then the Halcyon blog post is linked there as well.
Yeah, and one thing to note here, like Alden mentioned, we're going to be covering the ransomware binary itself. So if you go to that Halcyon blog, I think the binary starts with 4E. The protector binary we aren't going to include in this, but it's that binary that brought the vulnerable driver TrueSight and leveraged that to kill security solutions. So I highly suggest walking and looking at that malware as well, but we're focused more on the locker binary or the ransomware binary for this.
Sweet. So I'm going to talk about the attacker behavior that we observed in the instances where we saw Nebula deployed. Obviously, when it comes to stuff like initial access and lateral movement, those change and they're very situational. So again, take this with a sort of grain of salt, but this is just what we observed. So in terms of initial access, I believe the case that we saw, it was exposed RDP. And so the attacker was able to log into a host directly. From there, they used their protector exe rat to perform most of the enumeration and setup for their ransomware deployment. So this binary is in charge of basically evading detections, anything that would sort of hamper their effectiveness in terms of the actual encryption. But after that, they also were hands-on keyboard doing standard sort of establishing persistence things. So they were adding new users. They were trying to set up different ways of staying on the system, even though ideally the system would be pretty much useless post-encryption. But they were also doing standard sort of lateral movement, trying to enumerate the network and figure out if they could pivot and ransom other hosts in the network. Luckily, in the case that we saw, they weren't super successful in doing that. So they only got 1 or 2 hosts, I believe, which is fantastic. And then obviously the end of it is ransomware. That's kind of where they blow everything up. And then the host isn't going to be super useful, so they're out of there. So yeah, that was sort of the attacker behavior we saw. But in terms of general attack chains, they're probably going to look mostly like this. But again, they'll change depending on your situation.
Cool. So whenever I usually get a piece of malware, the first thing that I do, I built out this PE parser in PowerShell called PowerParse. There's a lot of PE parsers out there that are great. I know Matt Graber has created one as well. But there are just a couple of things that I always like to do initial triage of some malware. And that's what I built into PowerParse. So I ran PowerParse against this. And some interesting things that kind of point out here is that this is a exe binary. It's a 64-bit binary as well. There's only 1 PE in this. This is kind of important. There's a lot of malware out there that will embed multiple PEs and then separate itself upon execution. So that is built in for this as well, which I found pretty interesting. And then lastly, it will pull the TTPs or the techniques that are used. This is based off of a list of APIs that I know that correlate with specific techniques. And so if you look at this next slide here, we can see kind of the different TTPs that were executed. And there's some interesting aspects here. It creates a process somewhere, and it also will open a process, read some memory. Now, it doesn't mean that this is dumping LSAS directly, but it just means that these API calls are somewhere within this binary. And there was an attempt, in PowerParse, an attempt to kind of match those up with techniques that kind of matter. There's obviously is debugger present. That's common within malware. They just want to make sure they're not being debugged, and they'll kill off if they are. There's some Cobalt Strike and command and control APIs in here, which I found quite interesting as well. And then there's some ETW patch APIs, which we will dive into here in a little bit. Again, PowerParse was simply meant to just kind of get an understanding or lay of the land of what techniques are the malware is doing. This is nice for ransomware or non-ransomware malware, That way, whenever you are jumping into the malware, you kind of have a place to start. You can always start at the main function, which we'll do here in a moment, or you can just dive into the techniques that are actually being deployed and kind of see what it's doing there.
So Jonny, just before we move on, do you want to just talk quickly about why those Cobalt Strike APIs were so weird in this particular case, in the sense that they,
Yeah, we won't dive into it too much later, so it's a good point to bring up now. What's interesting here is that there was a structure that had these strings in it, these beacon function strings, and it point to a function where it was implemented. Like there was some stuff for like revert to self. That's common with like token impersonation, things like that. What's interesting with there is that you'll commonly see that with like obviously beacon shellcode or like generated stuff like that. But this was more embedded within this. So like you won't commonly see that within like a larger ransomware malware where it's embedded and then implemented. What's interesting too is that we found no indication that these functions were ever actually called. They were in the structure. You could see that. You could see some of the functions were implemented, but there were never actually any calls to these functions. We didn't necessarily dive into from a debugging perspective to validate that fully, but just inside of Binary Ninja or IDA, there was no cross references to that structure or that table, and none to those functions directly. Did you want to add anything else to that, Alden?
Yeah, I mean, I think that kind of highlights a general trend with this ransomware is that there's a lot of functionality that's included but never used.
Yeah.
So whether or not that's an indication that this is obviously a young threat group that is sort of starting out in ransomware, so maybe they're just sort of testing out different functionality to see what works and what's not good. It's quite strange, but it's definitely interesting to note. So there's some functionality that you'll see that we'll talk through that maybe, I think everything that we talk about today is used, but there is a bunch of other stuff that is included that is malicious and interesting. But given that it wasn't used and we couldn't see any like even indirect references to it, it's not super important.
There's also some functionality in here that's like not complete functions were thought through. Like we'll talk about ETW patching here in a little bit, but some of the functions, there's like one particular one that where they did everything you would need for patching except the patch itself, which was interesting. We found some of like incomplete functions within this malware ransomware variant as well, which was interesting to see. You don't really see that quite often. So if we want to dive into the malware, the first thing, like obviously whenever you look at the main function. We're not going to dive into the whole main function. However, what's interesting here, what I will point out is there is a jump table that gets created. And I made this joke to Alden, and I've made it to Jamie and some others. This wasn't what we like to call like ChatGPT malware or ransomware. A jump table like this is a C++ concept where it's like, I think they're also called dispatch tables, but it's simply just like a table that'll be built out. It's basically a bunch of function pointers. But that's the first thing that happens with this main function. And we'll dive into that here in a moment. It also will get like the program arguments. How it does this as well is quite interesting. It does it via an API, get command line W, and then passes that into, command line to arg, which also is another API. Depending on a argument that's passed in, it'll create a mutex. This is just to make sure that only one instance of the program is running. There's not multiple. It will, depending on the flags that are passed in as well, it'll kill a list of static processes and stop some security product services. And it'll get information about the system, and then it'll go and perform the ransomware. But this is the general beginning of that main function. And so we'll go ahead and dive right into the function table.
There's also one quick interesting technique here that I want to make sure we touch on before we move on, because if you're any of reversers in the room, you're going to look at it and be like, wait, they're not actually calling these APIs directly.
Yeah.
And so in the case of this ransomware, what they're doing instead is that they have a helper function where they'll essentially pass the DLL name and the function and then use that sort of different abstraction layer to call those APIs instead of doing it directly, which is a good evasion tech, or I guess an attempted evasion technique, despite the fact that the APIs are in plain text and you can still see that they're in there. It just means that they're not called in the traditional sense, which is, I guess, an attempt to make their malware a little more stealthy.
Yeah. you'll see a lot of, like, if anybody goes and reverses, you'll see a lot of get proc address in here. That's just a way for them to kind of, instead of directly calling those, is just to get like a pointer to that function within a DLL and then execute that. They do that a lot. That takes a lot of time to build out. So, I guess shout out to them for being very patient. So yeah, like what Alden said, it's very interesting that they do that. They do have a lot of helper functions in here.
Yeah.
Which made it a pain to reverse, to be honest with you as well. I mean, like a lot of these strings, although they're built out, what you'll see in some decompilations is that they're actually like hex values, and then you have to convert them over, and it's just kind of a pain. Binary Ninja did do a great job at like automatically doing that for us in a lot of instances. Other decompilation views did not do that for us. So this was. Do
you want to say which tool didn't?
I don't think it necessarily matters. I think we're
definitely. Yeah. It's not either or anything.
So if we dive into the jump table, the first thing that gets called is obviously this MW create function table. Now within here, there's just a variable that gets set. It's a global variable. It'll get checked to see, hey, did this already get done? If not, go ahead and do it. And then the value goes to 1 to show that it was done. But it essentially just calls MW build a function table. And then within here, what'll happen is it iterates through a table of function pointers, make sure it's built out properly, and then it'll go and actually execute those functions within that table. Again, this is very interesting to see. It's not very common. But what I assume the reason why this is done is that they have this table of functions. They don't want to call each directly, so they put it all into a table or the structure and just pass it through. None of them have like arguments you need to pass through. So it just is like, hey, rip through all this and make sure it's like all of the pre stuff that needs to be done on killing services or whatever it may be can be done. So here's an example, or here's what the internal function table looks like. Again, you can see it's a bunch of function pointers. What I didn't go and annotate each one. The one that I did annotate was on purpose. It's a jump into a build service task list, which we'll jump into here. And that just calls MW build service task list. So it's just, again, jump to jump with these function tables, which made it quite annoying, I would say, when reversing. So within this function, essentially what is going on here is it goes through and iterates through a list of static task kill commands. And these programs, these processes that it's going through task kill are very security related or things that could interrupt the ransomware itself. And they obviously do not want that. You can see that within this while loop here. This is going to create a variable struct and then store all these task kill commands within this variable so it can then later be called within this MW kill process services. Now, keep in mind, I mentioned this earlier in the main function. There is a flag, and Alden will dive into this in a little bit later, but there is a flag that says, like, hey, don't go and do all of this. So this isn't called yet. It's called in the main function after that argument is checked and see if that's there. It'll then go through 318 service names and essentially do the same thing where it stores it within this variable so that later down the road it can be called and used to change the configuration of said service and stop it as well, which is quite interesting. We'll talk about this in the telemetry and detection view, but I just want to very much point out the high volume of processes and service names that it will try to attempt to look at and manipulate.
Yeah, and if I could just double tap on that really quick. So the services that they're actually choosing to stop aren't all security products necessarily. There's a lot of stuff like SQL servers or hypervisors or things like this that are generally going to have some sort of data living in memory. So if you think of like some SQL database that has stuff living in memory, if you're a ransomware actor and you want to have maximum impact, if those pieces of data are living in memory and you execute your ransomware, which is encrypting stuff on disk, that doesn't necessarily mean that the data living in memory is going to get encrypted. So what they're doing is they're trying to get those programs to stop and dump all of that data to disk so that when they run their ransomware, it will actually encrypt the contents of the database fully instead of just missing some of the stuff that's living in memory. Or think of all of the other instances of programs that are doing something similar to that. So it's a way for them to maximize their impact.
Yeah, maximize impact, yeah. Yeah, thanks for sharing that, Alden. Good point. So this is that MW kill processes and services. This is really simple. It's going to take that array of task kill commands, and it's going to pass it through the system command. Think of this as system is going to call create process under the hood, but this is just a function that you can use that's very, very simple, and I'll pass in. I believe, maybe I don't. When you look at the task kill commands, it's cmd/c, and then the task kill command. So that's what gets passed into system there. Now, what's interesting here, I want to point out with the services, before it actually goes and stops the service, it'll go and change or attempt to change the configuration of said service to service disabled. This is very clever for this malware to do, because let's say a security product can check the heartbeat of a service, whatever it is, and it will turn back on after so long, right? We've seen this multiple times, or any other service like RMM services, things like that. It'll turn the service back on to make sure that it can work properly and there's no issues. So it'll change it to disabled and then pass in and go to attempt to stop the service. That way, again, once the stop is successful, if it is successful, it can't start back up. The configuration has been changed. And this is very interesting to see him do this instead of just trying to stop the service as it may be. And it's using normal API calls to do this, like open service W and change service config, etc. It's just using the normal APIs to do this. There is an alternative you could do. It would be a lot of work, but you could do this purely through RPC if one really felt the need and desire to do. The APIs work under RPC as well, but it would have been a lot harder to reverse if they would have made the RPC calls directly. But here, they just call the APIs directly. I'm going to dive into some interesting patching functions that we will dive into here in a moment. But before I wanted to give like a little bit of a background. So there are 3 different functions in here that will attempt to perform something called ETW patching. We'll call it function patching right now, but it does this for 3 different functions or functionalities. The first one is AMSI, so anti-malware scan interface. This is common for like VBS, PowerShell, .NET, stuff like that. If like AMSI will collect that scan, will collect that information whenever some of like certain interfaces are interacted with, and can present that, like say PowerShell executed and what the payload was or whatever it is. AMSI patching has been around for a very, very long time. Matt Graber wrote a great blog about this. Another function that is commonly patched is ETW event write. This is really just a safety. Let's patch everything that we possibly can for event tracing for Windows or any provider that is loaded within my process. And I'll jump into what ETW is at a high level here in a moment. But this is the lowest call that you can patch outside of NT trace event and NTDLL. And so this is commonly patched out as well, just to, and when I say patch, it's literally just changing bytes whenever the function call is made so that maybe it returns, or maybe like the code does not generate telemetry properly, or if it does, it's like some baffled or some jargon that's shipped off and it's not anything that's specific to the malware. Now, what was interesting is I found Windows lockdown policy was being patched, and I haven't seen this in a long time. The Windows lockdown policy is used to block potentially unwanted software that is running in memory. But they were trying to patch this out as well, which again, I haven't seen it in a long time. So when I saw it, I was like, well, this is kind of interesting. It's commonly coupled with AMSI patching. Now, to take a step back, ETW, event tracing for Windows, it is a telemetry mechanism that's built into the OS code flow. It's not considered a blocking telemetry mechanism. It's more of like inline. So for those that aren't aware, AMSI is a big ETW provider. There's ETW providers that will collect telemetry if you create a process, if you load an image, if you do something in the registry. There's just a bunch, Defender as well, like all of these different things. And oftentimes the way that is done is that code is loaded within your binary, your process, via DLL. And whenever it goes through said execution, there is going to be an inline jump to some type of ETW function, which is the provider saying, hey, collect telemetry for this thing. And so that is used by a lot of security products. collecting those so that they can provide or obtain insight into said activity. And this is very valuable for those products. Now, any provider that gets loaded into your e-process structure, whatever it is, it's living within memory of that you have access to. So due to that, you can go through and you can really patch out any function that you really feel the call to do. And so a lot of times, malware or red teams, whatever it is, they'll just go through and they'll try to patch out these providers that they know in terms of like AMSI and WLDP, patch those functions out directly so there's no issues. But, oftentimes what we see is more patching with ETW event rights, since a lot of the times, or the majority, if not all the times, there's going to be a call down to ETW event rights regardless. And so it's just like a safety of like, hey, just patch everything out that we can here. So again, super common within malware. That way the security products don't consume or cannot consume that data that you are performing. I did write 2 blogs on this. If anybody is interested that is watching, one is called Understanding ETW Patching, and then the other one is called Refining Detections, New Perspectives on ETW Patching Telemetry. So that's kind of a background. We'll kind of jump into that functionality now. So all of this all these, like inside this malware, you're going to see a very general like theme to this. They're going to call get proc address with patching. They're going to call load library on some DLL. Okay, that's just to see if that DLL, to make sure that DLL is loaded within memory within your process. It's then going to call get proc address on the function that they care about, and then just basically get a pointer to that so they know where it's at in memory. They'll then call virtual protect. And the reason why they do this, they want to change the protection value of that memory or that region of memory. And what we'll often see is that's changed to a value of 40 in hex, which correlates to page execute read write. That's just so that they can go into that where that places in memory, and they can change the bytes of that particular part. They can change that code. In that way, there's no issues, which is, they'll do that via mem copy very, very commonly, which we'll see here. And then they'll call virtual protect afterwards to change the protection value back to its original value. So if we look here at the AMSI patch, it's exactly what's being done, right? The AMSI DLL is being loaded via load library. That DLL is being loaded. And then AMSI scan buffers, a pointer to that is being gotten via get proc address. Now, kind of what Alden mentioned that earlier, there's a bunch of helper functions. They don't call get proc address directly quite yet. This gets passed into something called like another helper function. I named it MW execute function. And essentially it just passes in what the API name is, and then the arguments that it wants it to execute, which just made it a pain to reverse, to be honest with you. Like I had to go through all that. And so shout out to them for doing that for me. And then virtual protect is called, and you can see that value of 40 hex being passed in. And you can tell like 10 bytes are being allocated here for that function address. That's what the hex 10 is for. That then gets passed into mem copy. There's a function, or it basically points to what bytes need to be put in there. And that's what the MW patch AMSI is. Again, it's a value of 10 bytes. And then virtual protect is called again to change the memory back to its original value. This was what I was talking about earlier. There's some like functionality in here that's like half done, half not. So this is a good example. Everything's the same as what we just originally saw. It's doing this for NTDLL. It's doing the ETW event write, ETW notification register, ETW event register, all of these different things. And the value is being passed in, or the address being passed in, and the address is being changed, or the protection of that memory is being changed. You can see that there's 4 bytes that's being done, and then the value of 40 in hex again, the page execute read write. Now, what's interesting here is there is what they want to patch it with is right here. It's that hex value right there, which really just an XOR RAX. It zeroes that out and then passes in a return. What's interesting is no mem copy called here, so it's not actually ever patched. What happens afterwards is they basically just they change the virtual protect value, and then they just change it back. So there's not actually any patching being done, which was very odd, but so be it. And then with the Windows lockdown policy as well, the WLDP patch here. Again, this was very cool. I mean, the WLDP query dynamic code trust, that is an API that's used to check that digital signature of dynamic code. So they're basically doing that and then doing the same things you saw with AMSI and with the ETW, but here they're actually calling memcopy. And it's just, honestly, it's just calling a return value of what those bytes are. So it was very easy to see. And so they're patching that out and then changing that virtual protect back. We'll talk into telemetry and detection potential with that here in a little bit, but not quite yet. I'll pass it over to you, Alden.
Sweet. So as we mentioned earlier, like, this malware has a number of flags that they use to basically alter the functionality of the binary. This isn't all of them. This is just a subset that were easily seeable in strings, and I thought made a good sort of visual and leeway into sort of how we would identify what these flags are actually doing. But several of the big and most important ones, there's a no mutex flag, which at the beginning, if you remember, in the main function, one of the first things it does is it will attempt to create a mutex. It was a big, long, gnarly string. And the usage of this is basically to check if the ransomware had run before to prevent it from running again and encrypting the system like over itself. In this case, if you pass no mutex, it will not write that mutex, or it will ignore if the mutex exists and continue execution. So you can encrypt your system as many times as you'd like over and over again. The reason that they probably wouldn't want this to happen is that if you are a ransomware author and you provide a key, and if you've encrypted the system multiple times because maybe it failed, so you ran it again, or like it didn't, something wasn't quite right, you could end up encrypting the system in a way that you're not able to easily fix, which is not great in terms of like customer service, if you want to call it that. But it means that your decryptor isn't going to work the way you'd want, which is not good in terms of yes, and inconsistent dashes. That really bothered me too. So what Jamie's referring to is the fact that no mutex only has one, and then SD killer, exit safe boot, verbose, those all have two. Traditionally, like the single dash will just be like the shortened version. So you can see there's -v for verbose or -v for verbose. So someone who really likes man pages is definitely like shaking their fist in the audience. But the other ones, so SD killer off will basically not kill all of the defensive software or other sort of services that we're running. Again, this is functionality that was also included in the protection binary, that rat that was brought down before. So it may be the case that if they're confident enough that there's no security products running, there's no need to run all of those subcommands. And I'll talk about why that's a bad or good thing for detection purposes, bad thing for OPSEC purposes in a bit. And then finally, there's -verbose, which basically just sets the logging levels. So funnily enough, they do actually provide logging functionality here. I believe earlier on, I think it was the killing important processes and services slide. Johnny, if you mind just like bopping back there for a second. So you can see sort of like there's that malware message function where there's some format strings. So basically when the malware is running, if that verbose flag is set, those like detailed debugging messages are written to a file called NBA log by default, or it's you can specify which file you want it to be written to as well, which is great from like a debugging perspective. You can like just enable verbose and you can see it'll tell you what it's doing with pretty good detail. But those are sort of the big ones. There's also, if you pop back to the argument slide, there's a few other like all local backups strings that you can see net. And as has been a trend with this ransomware, those aren't actually used anywhere. They're included, but might hint at future functionality or something that they're planning for the future. But right now they're meaningless. All right, so now I'm going to jump into some of the crypto-related stuff. So with ransomware, one of the sort of critical things to identify is what algorithms or what strategies are they using to encrypt the disk. And so when you're first like triaging your ransomware, there's a bunch of tools that you can use to do this. But essentially, you want to look for patterns or cryptographic constants for particular algorithms. So since we're using Binja, there's a fantastic plugin called CryptoScan, which essentially will just like run over all of the binary, and it will attempt to look for these cryptographic constants and provide you an address for where these are found. And why this is useful is because in this case, you want to see like, are they actually implementing their crypto correctly? Because if not, that's a great opportunity for recovery. I'm not going to dive too much more into that, especially in this case. But for the astute in the audience, this screenshot should make you relatively excited. Essentially, in this case, we found that Salsa 20 constants were found, and also some ECC 25519 constants were found. And for sort of crypto background, essentially there's two major families of cryptography. There's symmetric crypto, where the key you're using to encrypt and decrypt is the same. This is algorithms like AES, DES, triple DES, like those are all symmetric algorithms. They're typically very, very fast. So I think nowadays AES is built straight into like Intel CPUs as like a function. So it makes these cryptographic operations extremely performant, which from a ransomware perspective is great, because you want your program to encrypt as fast as possible before there's a chance for EDR to kill something or something to go wrong. So typically those are favored for encrypting data. The other family is asymmetric crypto. And essentially that's stuff like RSA, where there's a public key and a private key. And so you need both in order to actually like encrypt and decrypt stuff, which is good from a OPSEC perspective, because if you encrypt using a key, like your public key, you have a private key. And so then that information is not easily decryptable because you don't have a private key. The same is not true for symmetric crypto, because the key has to be somewhere on the host while encryption is occurring. So in this case, what they're using for encryption is actually not Salsa 20, it's Cha-Cha. They're very similar algorithms in terms of structure, but the constants are the same. And so they're encrypting the data using Cha-Cha, which is a symmetric crypto algorithm. And then that key that is generated on the host is encrypted using a shared ECC algorithm. So they're basically protecting that key with their own private key, but there's some other stuff that sort of is not quite right about the way they've done it, which is good. So yeah, hopefully that sort of was a clear enough explanation of some of the crypto nuances in terms of ransomware. This is not, so the screenshot on the right is basically just a implementation of how you would build out your like value table for Cha-Cha. So there's essentially a table of values that you can use to, you'll like iterate over using the Cha-Cha algorithm, doing like encryption rounds. And the data will actually be like, I think it's XORed against the values in the table, if I'm remembering correctly. But it is not a particularly like secure algorithm. Like Cha-Cha 8 is, I'm pretty sure, like the worst of the Cha-Chas. Essentially, the 8 stands for the number of encryption rounds that occur. So yeah, clearly sort of highlighting their noviceness when it comes to writing ransomware, which is always a good thing to see. And then the reason that also finding crypto functions is useful is because if you aren't able to find a clear main function, or you don't have symbols that you can cross-reference, so like in our case, we had some flags. Those are really easy to find, and then go look for where those are used in the program, so you can sort of determine what functionality is. The same goes for crypto, where you want to find where is the actual like cryptographic code being called. So if you can find those constants, and then you can walk your way up to find where those are actually used, that's a really good way of determining which functionality you actually care about and which stuff is not so important.
Cool. So now we're going to dive into telemetry and detection opportunities as it relates to this ransomware. We want to kind of, whenever we do this, we want to look at observed activity and correlate that to telemetry, and then see what exists, and then see if there is something that we can implement from a detection perspective. The first thing I would say is that there were 829 different task kill commands that were run. if they were trying to kill security products. It's generally a good idea to look for high volume of process creations for a task kill perspective, or maybe from like a PowerShell stop dash process or anything of that realm, a high volume of those. That would be a very clear indicator. You'll notice here, but let me stop, and before I move on, I'm not going to mention anything from an encryption perspective or when the ransom was actually done. I would argue that if you get to that point, it's too late. So we want to kind of look at things that happened before that would give you some indication of said things happening. Looking for task commands of security product processes that relate to the products that you have on disk. I think that would be very good. I mean, like there's a lot of security products now that require PPL to stop. So maybe, for example, you would see a task kill command for that security product. That's weird. If it's in PPL, which is protected processes, it makes it hard to kill those things. And so if you go to try to execute that and you see that like that's coming from a root process, that'd be a very good indicator as well. Seeing all those service type changes in the registry, again, you could go look for registry set values for the service type to disabled. This would be a very clear indicator like, hey, something's going on here. Because again, remember, it sets it to disabled before stopping it itself. Now, there's not necessarily an event that you can use to see if a service was stopped. You could look at that via an RPC perspective, but again, that would be quite difficult. But still, the service type change would be very good from registry. There's actually a system event that you could ingest inside of your SIM or whatever it is from the Windows endpoint. It's a event ID 7040, which will tell you whenever the service type of some service was changed. Now, a while back, I wrote a blog on ETW patching and like looking at detections for that. It's very possible to do this. What you would have to do is look for multiple virtual protect calls on the same like region of memory. You'd want to look for that hex value of 40 being used, and then like maybe a lower version that was being called back from like an original standpoint. Now, there's the link to the blog there. What I will say, in order to do that effectively, you will have you or your security product will have to be consuming from the threat intelligence ETW provider. There is some like prereqs that you need to do in order for that to happen. You can't just arbitrarily do that. You need to be a PPL process, which I think you need to be part of the Microsoft MVI program, which I can't think of the name of things like Microsoft something initiative. I'm not really sure what the V stands for. I forget off the top of my head, but you would have to be consuming from that. And you would have to have some ability to correlate as well those two events that are happening from Virtual Protect. But there is a blog on that I've shared there if anybody's curious.
So as Jonny kind of touched on, there's a lot of like behavioral detection opportunities here. They are using like system and subshells to run lots of commands. On the right here, I've included a screenshot of like what this actually looks like in the binary, but essentially they're literally just command strings that they're iterating over and running. So in terms of like writing detections, if you're using something like Sigma, you can look for like an unsigned parent running some of these commands. Unfortunately, like task kill isn't inherently malicious, so there's a lot of potential false positives here, and it's like really difficult to write like a good hard-hitting detector based on these. But again, as Jonny said, you can sort of do some correlation and see like, oh, like are these running in pair or running concurrent or like, after one another really quickly? Those are all things that are really good to look out for. The downside here is that if you're doing detections and you're seeing that this program is running, that also means that ransomware is already running, which is generally like, not that you're too late, you can still intervene, but it is not the most, not the preferable place to find this. Ideally, you would detect much sooner in their kill chain where they're performing enumeration, they're adding their new users, they're running all those kinds of commands. That's like a great place to sort of try and focus your efforts when it comes to like ransomware detections. Obviously, that is like an idealistic way to think about it. It's not that easy in practice. That's a whole like detection engineering can of worms that I'm not going to get into today. If you want to roast my take there, feel free. Right. So but yeah, essentially, in terms of finding this binary, there's lots of good opportunities, but it is a little bit late if you're finding it here.
Yeah, and to that point, one thing that we find within ransomware often, not every time, like malware is going to be different across of who's developing it, but there are certain trends that we see. And a big trend here that we see is once the ransomware gets dropped to disk, the first thing is to get a lay of the land and then try to cut off any ability of telemetry or shipping of data that relates back to that ransomware off to some product. So that's why we see a lot of like task kills here. This could be done a bunch of different ways on the system. If you want to collect that, you could do that from like a driver perspective on Windows, from like terminate processes and things like that. Another thing is that you also not only see like from a process perspective, you see the service aspect as well. It's a big trend that we see. Now, oftentimes what we'll see, and again, we didn't talk about this binary within this, within this talk today, but you often will see like a vulnerable driver being dropped and like something being shipped to the driver to say, hey, go kill this process, due to the fact that like there might be extra protections on those processes as it relates to a security product. And the kernel is going to be able, a driver in the kernel is going to be able to just shut those down, no problem. So there are those trends, but the key here when it comes to detection is you don't want to wait until the encryption or the ransom aspect. Alden brought up a great point. If you see this, that means the ransom's running, like the timer has started. And a lot of this happens very, very quickly. Now, some of it will, last over a long periods of time, 7 days, whatever it is. But oftentimes it'll happen very quickly. So as soon as you start to see these detections, you start to see these correlations, you have to act quick and you have to act fast and you have to isolate that machine. Otherwise, you're going to get the spread across your organization and it's going to be pretty bad.
Yeah, so in this case too, like when we observed what the attacker was doing on keyboard, there was a lot more tradecraft that was very identifiable before we got to this point, which is very, very good. They were doing stuff like net user ads of really suspicious users and like things like that. And so when we were sort of doing our review of this sort of incident, that was sort of what we were focusing on in terms of like, which detections were working well for finding stuff before it was happening and which ones like, areas improvement.
Cool.
Oh yeah, and so this is just one more example of like some of the commands that it's running. This is used to disable safe boot, I believe, which is again a flag that you can pass to the ransomware if you choose.
Yeah, and it has to reboot. That's where you see a shutdown-r-t. Like a lot of times when you go and do stuff like that, you have to reboot in order for that to take place. So yeah, that's why you see that. Cool. Alden, do you have anything else before I talk about the road shows and some upcoming things we have going on?
Nope, I'm all good.
Awesome. Cool. So thank you for joining us today. We do have some road shows coming up here soon. Here's some dates that are, there's going to be one in Pennsylvania, Baltimore, etc. Hope to see people there. You can go register at huntress.com/events. And then lastly, come to our next Tradecraft Tuesday. It's on September 10th, Tony Black. He's another principal product researcher here, and our CTO, Chris Bisnet. We're going to be talking about SIMs, and in that we're going to talk about the importance of SIMs and things like that. And then October 8th, there will be another Tradecraft Tuesday as well. Thank you, everybody, so much for coming today. We'll stick around for a couple minutes. If anybody has any questions, happy to answer those. And then nerd out for a little bit, and then you guys can go about your day.
So funnily enough, Huntress was not included in the ransom binary, but was included in Protector, which is like weird, but.
That is funny though. That is not in that's in the Protector binary, but not in the ransom binary.
Yeah.
Let's see. Killing EDR telemetry by sandboxing it with the native Windows firewall util was the hottest while I was red teaming. Is that commonly observed, or has there been an evolution to kill telemetry? No, I mean, honestly, like the Windows firewall is probably one of the best routes to go if someone wants to kill an EDR. I mean, you don't have to directly interact with the EDR binary whatsoever. You don't have to interact with anything like that. It's very much still used. It's interesting. You can, whenever you set that in the Windows firewall, that gets set as a registry key, there's a little bit of a race condition that happens. It's like, how fast can you log that registry key and ship it off to the cloud before it actually takes place? Is one question. It's like, there's just a race condition there. But oftentimes what'll happen is whenever that is set, nothing will get shipped out because it does take the code a while to consume that event and ship it out after trying to not correlate, but add context to that event before shipping it. So definitely one of the most used things, probably one of the most effective still. So I like that technique just because you don't have to interact with the binary or services whatsoever. It's just you get admin, put the firewall rule and run. So.
Yeah, so my guess here is mostly just that they're new and they don't have, I don't know, maybe like they're not quite prepared like infrastructure wise to deal with full data like exfiltration and doing all that kind of stuff. It's hard to say for sure. Obviously from the binary, you can see that they're actively trying to develop and make their process better. So I wouldn't be surprised if they start doing it in the future. And it's also a case of like, maybe it's just not visible, right? Like we've looked for it, but given like all of the dark markets and stuff that exist and where people are posting and stuff is not in English, and there's a lot of sort of weird stuff that goes along with it. Ironically, they were on Twitter for a while, but they got banned. So thankfully.
How do we get started in malware analysis? Let me think. So a couple of years ago, I wanted to learn Windows internals better and understand code flow and all of that. And I do think reversing malware is one of the best ways to understand the OS, but also keep up with the up and coming trends and what's like realistic that's going to happen in your environment. I think it's easy to get caught up in like, it's possible to do X, Y, Z, but the question is anybody actually doing it? I read this really good book called Practical Malware Analysis. It's got a little alien on it, super old book. However, highly suggested. It's probably still one of the best malware. I mean, Alden's smiling. It's probably still one of the best books out there for when you want to get started in reversing malware.
In terms of fundamentals, it's like the Bible. Like
100%. Yeah. And after that, just kind of like kept doing it for the years. I will say reversing is one of those things that if you stop doing it for a short amount of time, your skills kind of start to get rusty and the timing of it gets rusty and it takes a little bit to get used to it. It's one of those things you have to continuously do over and over again. And the biggest thing I can suggest, if anybody wants to get in, Alden might have a different hot take than this, but if you want to get into malware reversing and analysis, the best thing you can do first starting off is understanding assembly and the disassembly of the malware 100%. Like the decompilation out there has gotten phenomenal. It really has. But like sometimes I can get kind of meshed. I mean, Alden and I saw it with this ransomware. Like there's some weirdness where like, what is this actually doing? So we jump over to the assembly and the assembly never lies. So like you'll be able to tell it that way. It's really good. Even whenever you go to debug, some malware, the assembly is really good. So although Alden and I think decompilation has gotten really good, I think we both agree that like when you start with looking at the disassembly and really try to understand that as well.
Yeah, it really helps, especially too, if you're like trying to understand why decompilation is the way it is, or like you're trying to clean up decompilation, you'll see like a bunch of like weird artifacts and you're like, why the hell is it like that?
Yeah.
And then you can pop into the assembly and you can see like, oh, it's because like the calling convention's weird, or like, something is like not quite how it should be. And that's all stuff that you can easily pick up pattern wise in the assembly, but like decompilation, you'd have to wrestle with and sort of be missing information.
Yep.
So yeah, I totally agree.
And the next big thing too is make sure you annotate when you start reversing. Like annotate everything, functions, comments as much as you can. I mean, like, one thing that like I think Alden and I both have done is like get really deep in the weeds of what's happening and then hit a function that we've seen before, and then we're like, okay, we have to reverse this whole thing because we didn't annotate anything. Yeah. And so, the worst thing you can do with malware is assume the best thing you can do is validate. So making sure you validate and then annotate along the way is the best thing to do.
Yeah. My big tip for like, if you want to get really good at malware, or like, even if you're getting into it, is like find a report from someone that they're analyzing some malware, see if you can get your hands on a sample, and then do the reversing process yourself, do the triage, do the analysis, whatever, and then see if you're arriving at the same conclusions that people in the report did. And if you didn't, like, try and figure out like, why did you arrive at a separate conclusion? Because like sometimes you might find that like the report is actually wrong, or like, you know, it's a really good exercise of like, can you get to this certain point in your analysis? And it's also good because like, if you don't know what the hell's going on, you can look at the report and be like, oh, okay, so like this function lives here and it's doing this thing. And it gives you a good idea to like, you know, what to look out for, I guess, in terms of like functionality. And then it also like helps because your pattern recognition then will get better and better. So after a while, like your intuition of like identifying like XOR encryption loops or whatever, those all, you know, will sort of become second nature after a while.
Yeah, and Jamie just said something that I was just about to say as well. One of the best things you can do is write a program, like a simple like hello world, and then just drop it in and reverse it. Because the cool thing about that is you're going to have symbols. So like you can remove the symbols from whatever, you know, you're using to reverse it, IDA, Benja, whatever it is. And you know what the program is supposed to look like, and you can validate when walking through. And then you're like, oh, I'm kind of confused. Load the symbols back up. And they're like, okay, this is what's happening. And like you start to get a trend and start to feel of those things. But you always, like, the biggest thing too is you want to make sure you test but verify. You know what I mean? And like validate what's going on, and try your best not to make any assumptions, because I've done that with malware and been pretty wrong. So the worst is being wrong. So I think protections you can set up in place against firewalls to prevent it from being used to block EDR. I'm sure there is, but like the problem with that is that like it's probably like it's not something I would necessarily recommend. The firewall is there for a reason. The access to the firewall is there for admins for a reason. I mean, you could potentially set the firewall to only be set by system, but then it's like that makes it really hard for admins. You then have to drop something. And my fear is if you give out, you're like, oh, you have to be system. It's like, well, how's an admin going to do that? They're probably going to run PS exec, and then PS exec then becomes normal. So you start with this trickling effect of like, we have to then go above and beyond, and then you have like these bad behaviors or bad trends in your organization, and it makes it hard. You know, I wouldn't say prevent, you know, I would say monitor and making sure that you know what your firewall rules are, and things like that. I do have some research and stuff coming out around the Windows firewall as it relates to blocking EDR. That'll be out in a little while, but yeah, it's definitely a tougher of the things to do, I would say.
Yeah, you can also, I believe that there's some Sigma rules that detect basically modifications to the Windows firewall. And that's a really good way to basically figure out if there's, you know, potential tampering or something going on. It might be Matt Kiley. I don't know if it is.
I was going to say, I'm not going to confirm it, but Matt confirmed it himself. So cool. We have 2 minutes. Does anybody have any other questions that we can help out with? What other ransomware perform similar to?
Lots of them, to be honest. Like the uniqueness of this ransomware is like there's basically not any. Off the top of my head, there was, oh man, there was one recently that was very similar in terms of it ran a bunch of like subcommands, but I'm so completely blanking on which one it was.
Yeah, I'm terrible at knowing the name of ransomware variants, but I will say I have reversed some ransomware recently that like there's just common trends with all of them, to be honest with you. I mean, it's to say one for one is hard to say, but they're, you know, how they operate, what they try to do to operate is all very, very similar. So yeah, I've definitely seen some probably in the past month that have been very similar to LukaLocker. LukaLocker was just very interesting as well, just because they had so many helper functions and sub functions, which made reversing, I mean, all I can tell you, just made reversing a deeper pain than it necessarily needed to be. So.
Oh, Ryuk is what I was thinking of. that ransomware is relatively similar, not necessarily from an encryption standpoint, but just from like a stuff that it does. Sweet. Well, if there's no other questions, I guess we can go wrap up. But if anyone does have stuff that they want to ask about malware analysis, this ransomware in particular, whatever, I think our emails are listed around in our bios. I think I'm also on Twitter.
Yeah, you can hit us up on Twitter. To the question, will Jonathan and Alden be doing the roadshow? I haven't been asked yet, but I would do it. So if there is a roadshow you would like me to come to that's near you, I can pass that up the chain. I'd be happy to nerd out. My Twitter is JSecurity101. I made it when I was a freshman in college, so don't come at me. And now I feel like I'm too deep to ever change the name. So sticking with it.
I'm there with you, pal.
Cool. Well, thank you, everybody. I hope you guys have a great day. And reach out to us if you have any questions.
Yeah, thank you so much all for coming.